Hi everyone. Today we're going to work on introducing what is called the central limit theorem in sampling distributions. This is one of the most important theorems in understanding in statistics, so we want to take our time and kind of wrap our heads around the theory about what's going to be going on. So we're going to be finding ideas about sampling distribution today and some of their properties. So we're going to go to this website. It's an applet. It's called Online Statbook, StatSim, sampling distribution. Okay, so if you type that into your browser, it's going to take you to here. Okay, and there's a whole slew of directions here, but basically over here on the left-hand side, you're going to click Begin. Okay, now it's going to take you to an animated applet that we are going to use so that we can become familiar with what exactly is a sampling distribution and what the central limit theorem it means. Okay, so what we're going to do is we're going to choose our population up here. You can see that our population can be normal, uniform, skewed, or custom. So you can make it all whatever you want. Okay? And then we're going to select skewed. Now all these directions are in your notes. Okay, so we're going to I'm going to walk you through it, and then I'm going to ask you to pause the video so you can work through this and see what happens. So we're going to choose skewed to start with, and then at the bottom two here, notice it says mean, and that's what we're going to do. We're only going to focus on population mean right now. And this is going to be our one of two sample sizes. So we're going to change this n equals 5 to n equals 2 for the first one. And the second one, we're going to choose 5. So it's already 5. So we're going to choose that. All right. And then we're going to click animate a few times and see what happens. So here it says sample, animate. Okay, so it's going to take a sample, a size 2. And we're just going to keep clicking the button and see what happens. Okay. And if you notice, this little pink line right here represents the median. Okay, we're going to keep doing that. And we just play around. All right, and notice the bottom one isn't doing anything, and we can keep going. Okay, so we're going to press the one that says clear lower 3. There we go. And we're going to click 10,000 SRS. Now means simple random samples. So 10,000 SRS. We're going to keep n equals 2 and equals 5. Wow. What just happened? These are 10,000 samples of size 2. Okay. And this is the means of all of those. And look what happened. Okay. We now have a normal curve. Kind of. And our parent population is skewed. Okay, so now we're going to change our samples. All right, so I want you to kind of observe that, take a look and see what about mean and median and standard deviation, which is listed as D, kind of make some observations. All right, so we're going to change our sample size to n equals 10 and n equals 16 here. Okay, do the same thing. Click 10,000. Ooh. Notice what happened now. Okay, write your observations. Okay, and we're going to do 20 and 25. Okay, take 10,000 more samples. Does you confirm what you said? Okay, all right. Now we're going to clear our page. Okay, clear lower 3. All right, and we're going to create custom. Okay, so we're going to make our own. So here I have a very weird distribution. And we're going to start with n equals 2 and n equals 5. And just start playing around with this. I want you to kind of create your own custom distribution. Take as many distribution samples as you want. Okay. I'm going to change that to 25. I'm going to do 10,000. Kind of write down some observations that you notice in your playing around with this applet. All right, so take a minute, play around in here, see what happens, write down some observations. Okay, pause the video and go ahead and do that. Okay, So now that you've had a chance to play and play around within the applet and take a look at what's happening, let's look at a specific distribution within. This was created using the applet. All right, so consider a strange population distribution from the Rice University sampling distribution applet. So there it is. Okay, so describe the distributions as n increases. So here's the original, and I couldn't get them to fit here, but take a look as our means go from a sample size of 2, sample size of 5, sample size of 10, and a sample size of 25. What happened here? Okay, if you notice, as we increase our sample size, and I'm assuming we're doing like 10,000 or 100,000 samples, our distribution goes from this to normal. That's really, really important because that tells us a whole slew of things. Okay? It kind of tells us that as you increase your sample size, okay, and take larger and larger samples of larger sample sizes, our distribution goes from being anything to being normal. Okay, so maybe we want to write that down. Okay? That as we take larger samples, many times, the distribution of sample means, okay, so remember these are all the means of size 25, becomes normal. So we say normally distributed. Okay, so that's really, really important. Okay, in fact, okay, that when a population distribution is very non-normal, the sampling distribution of the sample means. So in other words, we took a sample, we found the mean. We took another sample, we found the mean. We took another sample, found the mean, and we did this 10,000 and thousands of times, and we graphed them on the graph, that it looks approximately normal with a sample size even smaller as 25. Okay, so how big of a sample would be better? Okay, how small of a sample do we want to go? Right. So when the sample is large enough, the distribution of sample means is very close to normal, no matter what the original population looked like. As long as the population has yes, we can find a standard deviation. That is what's defined as the sampling distribution. Sampling distribution is defined as the probability distribution of a sample statistic that is formed when random samples of size n are repeatedly taken from a population. So in other words, we can have a set of 4 numbers and do sample sizes of 2. Okay, find the averages. How many times does that mean? I mean, we could create these sampling distributions. Now, if we're only looking at the mean, then it's called a sampling distribution of the mean. Okay, so this is when the sample statistic is the mean. That's all we're going to concern ourselves with right now. Okay, so there's some properties. It says the mean of the sampling distribution of the sample means, mu x bar, so new notation, is equal to the population mean. So the mean of the sampling distribution is equal to the mean of the population. Now that's huge, because now, even if we know nothing about the population and we take large enough samples many times, we can estimate the population average. That's huge. And the standard deviation of the sample means, omega x bar, is equal to the population standard deviation divided by the square root of the sample size. Okay, so in all of these problems that we're going to look at right now, we know that there's going to be some form of population standard deviation, that there's going to be a finite number that's going to represent that. Okay, now another word you're going to hear for the sample standard deviation of the sampling means is called the standard error of the mean. And that's kind of important. It's going to be something that we're going to refer to from this point on. It's going to kind of wrap our heads around where we're going to estimate the population mean. So these are all properties of sampling distributions. Now, what comes from there is called the central limit theorem. Central limit theorem basically says if you take a random sample size n, as long as we're bigger than 30, and from any population with a mean and a standard deviation, then the sampling distribution in the sample means is going to be approximately normal distribution, and the greater the sample size, the better approximation. So the theorem is allowing us to take sample sizes of over 30, and it doesn't matter what the original looks like. I mean, it could look like this guy that we had in our little demonstration here, and as long as we take large enough samples, over 30, many, many, many times, it's going to look like that. Okay, so that's really important because that is going to match up with our normal distribution or standard normal form. Okay. Now, if we take a random sample, so this is the second part. This has two parts. The sample size is drawn from a population that is normally distributed. So it's normal to start with. Then it doesn't matter what our sample size is. So if your population is normal to begin with, like ACT and SAT scores, then it doesn't matter what sample size we take many, many, many times. Okay, so the sampling distribution of the sample means, I want you to remind, this is important. You need to know that. So this was part of our property. So this is part of the central limit theorem, that the mean of the sampling distribution is equal to the mean of the standard deviation. That if I was interested in variance, which we usually only use variance to get to standard deviation. So this is the mean. Remember, this is variance. And then omega x bar is equal to omega over the square root of n. That's going to give us our standard deviation. Okay, so you need to know this. I'm going to put a little star here. We got to know this. Okay. All right, so here's the point of the central limit theorem. That if we have any population, doesn't matter what it looks like, here's our mean, here's our standard deviation. If we take sample sizes larger than 30, the graph is now going to look normal. Okay? And the more sample size you get, the more condensed, the smaller the standard deviation is going to be, the better approximation of your information. If our population is normal to start with, here's your mean, here's your standard deviation. It doesn't matter what the size of our sample is going to be, as long as we do it many, 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 many times, we're going to get a normal distribution. Okay. So there's no assignment for tonight, but I wanted you to spend some time playing with the applet, wrapping your head around the theory, because the theory is really important. If you have any questions, please let me know. And as always, staying in means we keep each other safe. Have a great day, guys.